Can I start? Good afternoon. I'm Bram Vanderborght from the Vrije Universiteit van Brussels, and I am a robotics professor. And in fact, I feel a bit a stranger during this conference because I have honestly to say that I'm not a Java developer. So don't attack me on those things. I'm even not a computer scientist, but I'm a mechanical engineer as a background. But I'm building robots, and in order to make the robots do what we want to do, we also need to program them. So honestly, when I look in my programs and others look in my program, they say it's more debugging into existence, and they're not the most clean programs, I have to admit. But yeah, we have a lot of pressure to make the robots work and publicize about them. But when I met Tasha Kahl, she convinced me to give a presentation here. And I think it makes sense to, when we talk about the future, to also talk about robots. And the reason is that there is a trend that more and more we want to connect our programs, not only in the virtual world, but also connected with the real world. And we see the success of many sensors, like, for example, the Wii controller, or, for example, the Kinect, which was one of the fastest selling products, that there is a question from the customers to connect the real world with the virtual world over sensors. And then it's also a logical step that we extend our computers with actuators so they can also manipulate in the real world. And then you have, of course, computers. And that's one of my main motivations, is this multidisciplinarity that is required to build robots. Because computer scientists usually have very nice programs and they can do a lot of things, but when they start to build robots, then it's some kind of sometimes crappy. So I think we need to combine a lot of those disciplines to make really good working robots. And I often collaborate even with outside the technical fields. I often collaborate with physiotherapists to make our rehabilitation robots, for which you will see some videos. And also I collaborate a lot with psychologists to develop our robots that will help autistic children. So I'm even scientific director in the psychology department in a university in Romania, so to see how these collaborations go. And now it also becomes more and more possible for you to connect with the real world. For example, Arduino or Raspberry Pi are very accessible to make also yourself robots. How it started, in fact, most of the robots we find today are the industrial robots that produce in the factories a lot of things. Like here, for example, you see the assembly line of a car, and you see that in these factories, mostly all the jobs are done by very advanced robots. So here you see, for example, typical tasks of the robot, like pick and place tasks, which are very boring for humans, or also sometimes very dangerous parts, like taking things out ovens and so on. So mostly robots are used for the so-called 3D jobs, which are named dangerous, dull, and dirty. And for example, here is a task which is otherwise for a human very dangerous. So these are robots used by the BBC to record their movies, and sometimes they're catched by the ice bears, and then you see what's happening to them. So I think it's quite expensive robots that are being taken by the other types. So sometimes they continue to work, and like you will see here, so so even the camera continues to work here. It's so all is pressure. So that's a really task where you really so, but the mechanism continue to work. So that are really the parts also like space missions where you really want to have robots going instead of humans. But the initial dreams of robot, and this is a very old movie, was once produced by the car industry, was that from the beginning people were dreaming of robots that were used in our house. And here you see, for example, this kind of robots where they give the robots a human shape and also human capabilities. But then we saw that the real robots, and the real robots are about developed 50 years ago, that they're in fact mostly used with non-human form and used in industry. But now we see that probably the next 50 years more and more robots will be used in our daily environment. So now is the trend that more and more robots will exit the factories and will enter in our daily life, and this in a wide variety of applications. For example, here you see Aibo, which is a robot developed by Sony and is used for entertainment purposes. On the left you see Claudia Mitchell. She lost her arm and now she has a robotic arm, and she controls it not by using joysticks or something like that. No, the computer of the robot arm is connected with muscles on her breast, and the nerves that normally go to her hand are with surgery placed on the muscles. So when she thinks close the hand, then those muscles will contract, the arm, the computer will detect that, and the hand will also close. So the motions are still quite basic, and most of her daily tasks are, she still do the more complex tasks she does with her normal arm, but the robotic arm helps her in her daily task. And this is of course starting technology, and we're getting more and more known how it works to produce better of those arms. Then you see PR2 from Willow Garage in the right-hand corner. Don't think yet that it exists for real, that you can have such a robot in your house to clean the house. And now my girlfriend is away for 1 week, so I would really need someone to do that now, because the apartment is getting more and more full. But this is still teleoperated. And in the right top corner, you see safety robots that guard the house, etc. So it is a trend that more and more robots exit the factories and enter in our daily life. And in 2007 now already, Bill Gates made an interesting analogy in Scientific American, where he compared the robotics industry with the computer industry from the 1970s. He stated that at that time you had big mainframes which were extremely expensive, and only a few companies had them. And then you had the computer geeks that were making on those screens their own computer programs, and all the rest of the world was thinking, what are you doing there? And also the first computer games appeared. They were very simple, like Pong and Tetris and so on. And when you see to the robotics industry now, the very big successful companies are producing robotic factories to produce, for example, cars. Then also some hobbyists are building their own robots. They're very basic, but we're trying to do so. And also when you have the entertainment robots, like for example Furby, maybe still a lot of you know them from 10 years ago. Well, Hasbro is developing a new one. I think in a few months the new Furby will appear with also play and so on. And I have different of those robots at home, and honestly I have to say that they're not doing a lot, and after a while you get bored by them. But if we see that now in every pocket we have a cell phone with a computer capacity bigger than at those mainframes, that now everyone has a PC, and that the computer games are so developed, then it's maybe also not unthinkable what will happen with the robots that we are knowing today. So there was the dream of Bill Gates to have a computer in every house, but now maybe the dream is to have a robot in every house. And there are already some countries, like for example South Korea, that really want to target they want to reach this target. And there are many market predictions that say that the robotics industry will soon become bigger than the computer industry nowadays. But we also target the same difficulties as the computer industry at that time. First of all, we have no programming standards. So during my career, I traveled a lot. I went to Japan and to Italy and so on. And every time when I need to work with a new robot, and you will see some robots which I worked on, I every time need to learn a new programming environment because every robot has its own standards, which is really annoying because it makes that there is little reuse of code. So for my PhD, I made a walking generator for a biped called Lucy, and then I went to Japan and I worked on HRP2 that you will soon see up, and then I have to write everything again because there are other standards. Also, the standards for hardware are not yet fixed. If for a computer, we want to have a webcam or something like that, it's easy to connect. If I want to have another sensor on my robot to do something, then I need to make my own electronics and to connect this sensor to my robot, which consumes a lot of time, and of course that leads to delays in the process. So because there are no programming standards, many of them want to become the programming standards. So you see Microsoft, if Microsoft Robotics Studio, you have Oracle's OpenHRP3. You see that there are many now. ROS is becoming, Robot Operating System is becoming very popular. So there are many standards, but there is not yet one or two or few winning operating systems, which makes it difficult to produce robots. But why is this evolution happening now? I think there are a number of reasons for that. First of all, a very important reason is that there are many cheap and small sensors available. If you look, for example, to smartphones, how many small and cheap sensors are in this small device, that makes that also all those robots, they need a lot of sensors to hear, to feel, to see, and so on. And with this evolution that those sensors become smaller and cheaper, makes that we can implement a lot of sensors in the robot. Also, it's very important for us that the computer power continues to increase. When we want to operate a robot, we need to have everything real time. When you speak to the robot or when you touch the robot, it doesn't have time to think 1 or 2 minutes about it or even a few seconds, because that makes the communication very problematic. Moreover, you have to know that, especially mobile robots, the computer has to be on board. Some things can be done off board, but things has to be done on board, and it has to process both its function of the motors, the hearing, so the audio, the video, all of that has to be processed real time. So, but luckily the law of Moore is still valid, so we can take benefit of those continued power increase, computational increase. And also a very big thing for us is, I think, that the markets are coming. And a very big market is probably the aging population. So here you see a graph of the predictions of the amount of people that will be more than 65 years old. And you see that especially Japan has a huge increase in aging population. So in 2030, more than 30% of their population will be older than 65. And this graph is in fact the main reason why you see so many in the media, so many robots coming from Japan, because they think that part of the solutions to take care of this huge population is robots. Not all agree with that, to put a robot with grandfather or grandmother, but in Japan there is less objection to use robots in their population. So probably the robotics will be the next revolution. So in the beginning we had the analog wave, then we had the PC coming, so it was the first digital wave. Now we started to connect all the devices together over the networks and so on, so that was the second digital wave. And probably that will also, now we see the initialization of the robotics wave. And it's in fact logical, I think, when you see that also computer starts to have more and more sensors, then it's a small thing to also add motors so it can both sense, think, and act in the real world. But to make this evolution happen from industrial robots to personal robots, we need a lot of new technology. And on the left you see some videos from industrial robots. And what are the characteristics for those robots? First of all, they have to be incredibly fast because you want to have the jobs very fastly done. Also, they need to be very accurate. So, for example, welding or placing components, it has to be micro or maybe millimeter resolutions. And it has to also to be very strong. Usually, they're used to carry a lot of heavy goods. But there are requirements that are not at all required for personal robots. We don't need that our robots are very fast or very accurate. I mean, when a robot places a cup, I don't think we will expect from him that it's a millimeter resolution to put it on the plate. So other characteristics become very important. First of all, I think they need to be intelligent. One of the problems of those robots that will operate in a human environment is that it's dynamic and unknown, while in industry, in a factory, we can make the environment for the robot. So that means that we know from where the goods are coming and where you need to place them. While in a human environment, I mean, there can be a lot of obstacles, there are other persons, so it's a very dynamic and unknown environment for the robot. And the robot has to reason in this world and to find solutions out of it. So that also means that we cannot foresee everything, all the different environments in which such a robot can come. For example, your house is completely different than my house. But anyway, in those two environments, the robot has to be able to operate. So learning will also become very important for robots. It has to be autonomous, so the robot has to do all the things themselves. And of course, because we want that they operate in very close collaborations with them, safety is of course the primary concern. And here you see a video of Asimo, which is developed by Honda and which is still nowadays one of the most advanced robots in the world. And if you want to see him live, in April we organize a robot contest for children, and then also Asimo will perform in Technopolis in Mechelen. So if you want to know more about it, then you can surf to robocupjunior.be, and there you will find more information. So although this robot is very nice, when there is going something wrong with the robot, and my video is not. Yes, so when there is going something wrong with the robot, and you have to see what's happening now with Asimo, when it falls back, it's a really very hard metal thing that falls. And I have to say, this is one of the few examples that Asimo in fact really failed. It's an amazing, reliable robot. It gives a lot of shows worldwide, and only a few times it crashed, so the engineers that built this robot did really an amazing job. But when it falls, you see that it's in fact not very human-like. If you see what the human body is capable of doing, then it's really very amazing, and the robots are still far, far away from this. The main difference is that, in fact, Asimo and so on is built by technology coming from the industrial robots. And there we wanted to have strong motors. So when we control our robots, we need motors, and motors drive with a very high speed and with a low torque. But to power the joints of a robot, we need high torques and low speeds. So we use a gearbox. But this makes that this gearbox makes that the joint is very stiff. So although it can move very fluently, when we try to influence the trajectory of those robots, it's impossible. He will try to achieve that motion anyway. While in a human body, we have elasticity, so our body is compliant. And this compliance is very important for safety. When I bump into someone else, he behaves compliant, and this shock isn't as hard. Also there, when we fall, we protect ourselves because we fall compliant. Also, to absorb energy, we use our muscles, and that's why it's possible to jump from such huge heights, because when we touch the ground, the shocks are absorbed by the elastic components of our muscle tendon. And also when we run, we store energy. For example, when we hop, when we touch down, we store the energy in our springs, in our muscles, especially the Achilles tendon, which is released during the next hop. So that's to say, when I talk about the new generation of robots, many think that it's only, yes, we need to improve artificial intelligence and video and audio processing, but it's also we need to do a lot on the body of the robot. And for example, making compliant actuators is one of the key components in our research group that try to mimic the human muscles. And when I talk about safety, then this is a nice video. It's modern times from with Charlie Chaplin, and you see that at a certain moment the system starts to in overdrive and it becomes very unsafe. So safety is really a primary concern when dealing with robots. And this is of course an animation, a video, so it doesn't exist yet, but this is a real video. It's industrial robots, and it's cracking a coconut. Why a coconut? Well, to crack a coconut, it's about the same force you need to crack a human head. So never go in close contact with those robots because they have no problems to kill you. And that's also the main reason why those industrial robots are kept in cages, and when someone enters this cage, the whole system shuts down. But this is of course not the purpose that we want to have for our next generation of robots. We want that we can collaborate with them, we want that we can touch them, that we can wear them even, so safety is of primary concern. So a lot of researchers in the world are now dealing with this issue, and here you see a video, a very nice video of DLR, where they did a lot of programming. The whole dynamics of this arm is programmed in this robotic arm, and they have a lot of sensors in it, and when there is something wrong, the system automatically becomes safe. And that is Sami Haddadin. He's a good friend of me, and he was really very persuaded that his algorithm works well, that he even was very enough confident to use himself as a test person, because the initial trials were of course done with crash test dummies. What we do, and the right video is a video of a robot we developed, is that we also want to have the safety in the hardware. So on the left video, the safety is in the software, so all the calculations are done in the software. We also want to have safety in the hardware, and that's why we use those compliant actuators. So when you touch one part, then it's the inertia is decoupled from the rest of the robot, so you don't feel the complete mass of the robot when there is a collision. And what we use here is a kind of air muscle, so those bellies that you see here, when we inflate it with pressurized air, the muscle will contract and it will generate forces. And since the muscle, like a human muscle, can only contract, can only pull and not push, we need two muscles in an antagonistic setup in order to have a bidirectional working joint. But of course, what is the big dream of all people working in robotics is of course to build a robot with the same capabilities as a human, and also the same appearance often. And here you see a part of the video of iRobot, where a future is given where robots are completely integrated in our society. And of course, because it's a Hollywood movie, a lot of things has also to go wrong. So I hope we will get once to this kind of stage, but we leave the problems away. And then often I get the question, okay, why in fact do we need a humanoid robot? And in fact, a humanoid robot is one of the most complex machines to build. First of all, because it has two legs, the stability is very problematic because the center of gravity of the robot is quite high. It's about at the hip. The feet are very small, so the robot always has to balance so it will not fall over. So maybe it's much easier to use wheels because that's much more stable. But the problem of wheels is that a lot of stairs, then the robot cannot negotiate, for example. But then you can also think, okay, why not 6 legs or 4 legs, which are more stable, but then the robot has, for example, problems to turn, for example. And we also want that the robot is able to use the same tools as we do. because otherwise you need a drilling machine, for example, for yourself and one for the robot. So that also makes that you need a robot with hands, for example. And it has also to be big enough so it can turn off and on the light, for example, or can reach a table so it can put things on the table. So very fast, in fact, you come to have a robot that has the same appearance and functionalities as a human if you want to use it in the same environment as a human. Because our complete environment is optimized for humans, so probably the machine that is most suited to work in this environment is also a robot with the same appearance and capabilities. And here you see 2 videos of robots I've been working on. So on the left you see HRP2, it's a Japanese research platform, and there my task was to let the robot walk over obstacles. So when you walk over an obstacle, you need to increase the step length, and then of course the robot has more chances to fall. And then you see we programmed a lot of features, like for example the hip rotates, so we have more space between the legs. And also we let the arm swing to the back, so we can even make the leg go more to the front. Because the reason that we had also a lot of problems is that the design of the robot is very nice, but not so suitable to walk over obstacles. And the reason is that this robot is designed by a manga illustrator, which is a popular comic strip in Japan. And you see this device in the back. That's more a safety device. So it's in fact a patient lift that we use. The reason is in the beginning you have always bugs in your program, and when this robot crashes, then the patient lift supports this robot. The reason is that such a robot costs 400,000 euros, so I didn't want to explain to my boss there that I broke the robot due to the software error. And also you see the 2 nice ears that are very nice, but the wires regularly make them pull off, so it's a bit annoying, those ears, although quite nice on the manga. And on the right, it's a European robot. It's called iCub that I worked on in Italy. And as I said, balancing is a problematic for robots. Here we also used compliant actuators in the legs. And then you see that we were disturbing the robot a lot to see how far we can go when it doesn't fall. So the robot has a balancer inside its body to balance when we were disturbing it. So one of the problems of humanoids is you will not see them very soon in your environment, and one of the big issues is their price. So iCub costs about 250,000 euros, and I think that's only components, so then you don't have yet the cost to assemble them. HRP2 is 400,000 euro, and then you have for 5 years such a robot. And Circles, it's a hydraulic humanoid, even costs 1 million euro. The reason why they're so extremely expensive is that they're only produced in a few quantities. So all the parts, and there are a lot of parts in such robots, are produced by hand, which makes that they're very expensive to make. So I often compare the price of such a humanoid robot with a very expensive Ferrari. Also, such a car is mostly made by hand. But I think if you have good applications for robots, and the markets are ready for them, so then I think the price of such a robot can drop to that of a cheap car. And why I think that this price can be reached is that the number of components in such a robot and the complexity to produce it is about the same as such cheap cars. But then it's really necessary to go to mass production of them. Another reason why we don't see robots yet in our society is that, in fact, they cannot do yet so much. I often compare the mobility of such a robot with an 80-year-old person. Because when Asimo comes, he needs a perfectly flat terrain. There may not be bumps in it, because that's already problematic. And also, for example, if you saw Now, it's a very nice platform. It's a very nice French company that's already sold thousands of those robots, mostly for research, also for education. But also there it has still a mobility problem, so we still need to work on that. And also the intelligence, yeah, we can discuss about the real age, but the robots are not yet so intelligent. Even basic commands like go to the fridge to take a can, already that is a huge effort for the robot to let him do such things. So that's what we often see, that people have huge expectations about those robots, and I think it's often fed by what they see in movies, but the reality is sometimes different. But I think by working hard together and in multidisciplinary teams, we will be able to manage this situation. And if you see, for example, the advances of the Google car, like 10 years ago, there was a big contest, the DARPA challenge. The winner didn't even succeed to succeed 5% of the total trajectory in the desert. And if you see now the videos of the Google car, they've already driven thousands of kilometers in the neighborhood of San Francisco. So this technology in 10 years really improved a lot. So which robots are then already a commercial success often? That are often the robots with a very niche application. For example, the vacuum cleaning robots, or robots to clean your pool or mow the grass and so on. And also the entertainment robots are becoming more and more successful, and here you see different examples. Also, for example, the Lego Mindstorms. It's very nice what you can all do with this simple set. So the numbers are increasing. I think for the vacuum cleaning robots, iRobot already sold 7 million of them, and millions of them. And here you see such a vacuum cleaning robot. It's not at my house, it's a YouTube video, but it's pretty funny. So if the robot has obstacle avoidance, but if the cat helps a little bit, it can reach all places. So also at my home, I use such kind of robots, and it's really doing a very good job, but I had to adapt a bit my apartment to it, so I have no stairs in the apartment and so on. So that makes it much more easier for this robot to work with it. But otherwise, it's really doing a very good job in my house. I never touch a vacuum cleaner anymore. So, yeah, the job is done. Normally, it goes back to its charging station automatically. So the future trend is that we want to get the robots out of the factories and out of the cages, and that humans are able to collaborate with them. So I think the future robots is not, and that's often also a comment that I get, especially in Europe, but robots will take our jobs away. First, I don't think so, because I think it's more the purpose that we need to collaborate with them. And here you see the founder of Rodney Brooks. Is a very famous robotics computer researcher, and he founded iRobot. So the vacuum cleaning robots are produced by his company, but also, for example, the military robots that are used in Iraq and Afghanistan, like the PackBot, are produced by his company. And now he has the new company, Rethink, and they've recently announced the Baxter robot. And there is the idea to have a robot, and it's cost $22,000, so it's quite cheap if you compare it with those current used industrial robots. And there, the idea is that also small companies can use this kind of robots. Often they have not the programmers in-house to program these robots, and also small companies have too slow quantities of products to be handled by the current classical robots. So what he developed is this Baxter robot, and there the idea is that you can just demonstrate to the robot what he has to do. So you grasp his arms and you say, okay, these components need to go there, and the yellow parts need to go there. And after a few iterations, the robot learns what he has to do. But because we want there, you see that there is there a very close collaboration wanted between the robot and the human. And the idea of Rodney Brooks is that we can, as such, take back the production of China, where it also becomes more and more expensive. And here we see that the production is nearly going away out of our countries, that he wants to keep them back by using robots which are very cheap to use. I think he calculated that it's about $2 per hour that it costs to use such a robot, so it's very cheap. So he hopes as such we can again produce products, but then in close collaboration with these new types of robots. And you see the robot has also a face, and I think also communication is very important when we want to have a good collaboration with humans. So when we communicate now with machines, then we need to use human-centered communication channels. So we use a screen and a menu and a keyboard and a mouse, and I assume that all of you have totally no problems with that, but for example, my grandmother and so on, she has a lot of difficulties with, even with the remote, for example, because it's not human. What is human? Human is like speech, emotions, and gestures. And on the right, you see a part of the Disney movie WALL-E, and although there is no sound, and certainly no speech, I think everyone in the room understands what the robots want to tell us or what our feelings are just by emotions and gestures. So I think also for the new generation of robots, and when you see, for example, the robot of Baxter, also there, those non-verbal communication channels become very important. And psychologists even show that the majority of our communication goes over non-verbal communication cues. Verbal communication cues. So in the lab, we developed a social robot Provo. If I can start the video. So it's developed to study the human-robot interaction, especially with children. And the robot has 20 degrees of freedom in the head to show different facial expressions. It has also a camera in the head. So, for example, it will look to the person with who is interacting, because that's socially accepted. When you talk with someone, you look into his face. That's the Provog. It's the derived product. I will show you later some more videos about it. So here you see a bit the internals, so the eyes, the eyebrows, the ears, and so on can all move and have their dedicated motor. Then we have also touch sensors under the skin, so when you hug the robot or when you squeeze too hard, the robot feel pains. Again, because we want to use it with children, safety is a primary concern, so all the parts are again compliant, and we also wanted to create a very soft and huggable robot for the children. So other robots are very stiff, but it's not so very soft to hug. So that's why we all use those compliant elastic actuators in the robot. And then the robot can show different facial expressions by moving like surprised. And so you see that the eyes and the eyebrows move. Also the lip corners move to show different facial expressions. And for example, yeah, we wear them. Usually engineers like more the inside, but to do tests we have to cover him. And here, for example, the robot is greased in his trunk and he's first surprised and he's angry. So the children have to hug the robot a bit so he becomes happy again. So for what do we use this robot? Well, we use it for robot-assisted therapy. So for different therapies, they started to use animals, and they showed that animals have a positive influence in different therapies. But the problem of animals is that they're quite difficult to control, to program, let's say. They can also bite, or they're sometimes unhygienic, so they're not allowed in hospitals, for example. So the idea is, okay, why not replace the animal with a robot and to do robot-assisted therapy? So that's also one of the reasons to develop Provo. What I also forgot to tell you is that we give Provo an imaginary look. The reason is we could also have like copied a dog or a cat or even maybe a human, but the problem is then that the children will expect the behavior of a dog and a cat. And that's not always what the psychologists want in their therapy. They want that they can do what they think is good for the children. So that's why we gave this robot an imaginary look. So everyone recognized that it has a mouth and eyes and so on. So the social communication cues we understand, but what is the exact behavior of Provo that can be that's unknown by the user, so we can give it its own behavior. So we use at the moment the robot-assisted therapy for autistic children. Autistic children have problems with social interaction, and they prefer computers and robots instead of humans. But because they have those problems with those social interaction, they have also problems engaging in our society. So those children often get many hours of individualistic therapy a day, which is of course very expensive, and it requires a lot of workforce. And that's why the idea grew to start using those social robots with them. And here you see a video where the robot is interaction with the children. So this is typically an habituation phase. So the children are allowed to ask questions to the robot, so like, do you like chocolate and so on, and then the robot responds. So this is in Romania because we have this collaboration in Romania. You see that the children are really willing to touch and kiss the robot. At the moment, the robot is not autonomous, so there is supervised by a psychologist, and she's sitting in the back. You saw her, so she's reacting to the behavior of the children. So if the children ask a question, at the moment for us it's still too difficult to really understand this question by the software, because the audio processing is not yet enough developed, so then we just push the button yes, no, or fall asleep like the robot will do now when he's singing a song. So this we called Wizard of Oz experiments. So a human operator controls a robot, but for the children, if it is like the robot is acting autonomous. And so the idea is that we will gradually increase the autonomy of the robot so that it's only supervised by a therapist that this interaction can be done. So what are the typically experiments we do with the children? So one of the therapies with the children is social stories that are very simple stories how to behave in a certain social interactions. For example, the children have problems with saying thank you. For us, it's very normal to say thank you, but for them, it's not something so obvious, so the children don't say it, and it's often the parents don't like it. So then, for example, the parents told us, okay, learn the children to say thank you. So then there's a social story, like if you are saying hello, for example, and then we have, for example, in the morning when you see your mother, you have to say hello. She will feel happy when you say hello. She will be sad when you don't say hello. And then the robot also shows the according facial expressions. And then we create a social opportunity for the children to use what they have learned. For example, this was for saying thank you. So for example, here there is such a toy PC, but the batteries were wrongly connected. So the child asks, can you help me? And then the therapist correctly installs the batteries, and then we measure how long it takes for the child to say thank you. And then, for example, if we had to use verbal cues or gestures, like then it's worse and worse. So then we compared with the human, and we saw that when using the robots, the successes were higher. And also that was what the therapist said to us, that the children were much more interested in the robot than when they were telling the stories. So we hope as such to use the robots to engage them in better social interaction. Another experiment we used, you see here on the right, those children have problems finding emotions when something happens to someone else. It's called part of the theory of mind. And so what we did is we created animations on the belly of Provo, for example, going to the zoo or eating an ice cream or falling, and then they had to tell us how was Provo feeling. And we saw that with an active phase of Provo, the results were also much better. Then I also already mentioned the idea of Provogochi. So Probogotchi, maybe you still know Tamagotchi, the small eggs that you had to feed to keep it alive. Well, this Probogotchi is in fact the same idea. And in fact, we came to the idea when we had to go to a science exposition and the robot was not yet finished, but a lot of the software components were already finished. So we designed this game. So we bought in China some dolls of Probo. We opened it, we put a lot of sensors in it, like touch sensors and RFID tag readers. And then we have a virtual representation of the robot. And the robot has some internal needs, like his hunger, he needs love, he needs hygiene, and so on. And you have bars which show those internal needs. And based on those internal needs, we calculate the arousal and valence. And arousal and valence are the basic components for your emotions. So then for example, you can hug the robot, but when you squeeze, the robot will feel pain. And you can also feed it. So you give hamburgers to eat, and then with the hamburgers, his hunger goes down. But it's bad for his health, so it's better to give fruits and so on. And we use it with autistic children. Often they have problems with playing together with their sibling. And as such, we created a more pleasant opportunity for the children to play with their brother or sister. So they have to exchange cards and so on. So these are possibilities of using the robots with children. They're also a lot used with elderly, so that's especially research that is done in Japan, but also in the Netherlands and so on. They're busy with it. So here you see that robots are used with elderly. There was also the Dutch company Philips that produced the iCat, and they also did experiments with humans. And here it's in Dutch. It's quite funny that you see that the interaction is not going so well.
Je moet wel een beetje harder praten, hoor. Wat is uw naam?
Ze zal zich eerst even voorstellen.
So they say that the robot will present himself.
Hallo, ik ben Phoebe. Wat is uw naam?
So she asks what is her name, and she asks what is her name, and she says that it's speaking very unclear, and it comes to the background noise.
Wat kan ik voor u doen?
So the robot asks, what can I do for you? And the woman says that I want that you teach to speak a bit louder, and the robot says, I don't understand you. And then the other says, what do you say? So it comes to a very funny interaction. So she wants that the robot talks a little bit more clear. So just to show that it's really important that when we want to develop such robots, that this human-robot interaction goes very fluent, otherwise that will lead to a lot of frustration. So this was the cognitive human-robot interaction that we do in our lab. We have also a physical human-robot interaction, and that is mostly for gait rehabilitation. So I started with my PhD with walking robots, and then we thought, okay, why not extend this to help people that lost the ability to walk? And here you see a patient which has problems to walk. So you see in the left-hand corner that he has problems to walk. And often his therapy is then, in some situations, like when the spinal cord injury is not complete, or like, for example, after a stroke or some MS patients, they can really learn to walk again. So that means the nerves are not... Oh, it stopped working. The nerves are not static, but are kind of reprogrammable. But then what you need to do is to do over and over the same motion again. So what do therapists do? They take each one foot and they do over and over this motion, and one is holding the hips. So it's clear that it's very exhausting, very expensive to do so. So in Belgium, no rehabilitation center is doing that. So that really is a very nice application for robotics, where you go into an exoskeleton and this exoskeleton then walks, and as such you really learn the ability to walk. This device has only the knee and the hip activated, but not the foot. And sometimes the problem is that the foot goes under the belt and that the patient breaks his foot, so that's a disadvantage. So we will develop a new robot where we'll also activate the ankle. Another problem is that you see that the patient is in a harness and that is lifted, so the patient doesn't feel the complete weight through his legs. So we want to develop a robot that can completely take the weight of the user. And also, when walking, we also do the left-right motion, which this robot doesn't do. So that's also an innovation we want for this kind of robots. But because it's such a complex machine, oh, the media is not fine, sorry. So we developed a knee exoskeleton because these robots are very strong, because we have to support the human body, and so we have to go up to 100 Newton meter, which are quite a lot of torques. If they are wrongly used, then you can create some damage with the patient. So that's why we investigated first the knee exoskeleton, and we tried it with MS patients to see how it improves. And now we're developing this complete lower limb exoskeleton, which has 12 degrees of freedom. And one of the main ideas we also have is that the previous robot is kind of industrial, so it has the stiff actuators. So I also set ones in such a device, and it really works for you. So you don't need to do any effort to walk. And then we see that it's no use to use it, because then the nerves are not trained to do this motion, because it's just walking for you. So we want that the robot only supports there where it's really necessary to put as much of effort in the patient. And then we use those compliant actuators which I presented in the beginning. There's still a lot of other applications where those robots are useful. So for example, in paraplegic persons. So for example, Mark Hermans, and I don't know if you saw a few, I think 1 or 2 weeks ago, the Telefax documentary where Mark Hermans is a very famous triathlete who got paralyzed after a training session, is using such a device to walk again. Also, they're using for example, assist people with the usual forces, but to, for example, nurses that have to lift patients out of the bed. In Japan, they're developing the HAL exoskeleton, so they can take the force through the exoskeleton to take the patients out of the bed. And in the United States, also they're developing this technology, but there it's mostly to make super soldiers. So they want that the soldiers are able to wear a huge backpack and still are very mobile. So there the exoskeletons are mostly developed for military reasons. But the good thing is that they also make derived products, like for example those exoskeletons to help paraplegic persons. So the origin of this exoskeleton comes from military purposes. Then we're also developing prostheses. So walking with a classical prosthesis is it's like walking with closed ski bows, because the ankle is immobilized. So the gait is not symmetric, you consume more energy, you walk slower, and so on. And that's why we try to implement robotic technology to make better prostheses. And so the main idea here is that the spring is a very important part in those prostheses, because when we walk, we store a lot of energy in our Achilles tendon, which is released during the push of the prosthesis. So like that, we can use less energy to make this robotic feet walk. So here, for example, you see a prosthesis that we recently developed, and the ankle needs huge motor. In fact, the torques are about 140 Newton meters, and we need peak power of 240 watts. So our ankle has a really very strong energy burst needed. And to do that with a classical motor, we need a very big motor, so that we cannot place out the ankle. So what's the idea in this prosthesis that we developed? Well, we store energy in a spring, so during the walking motion, we store energy from the motor in a spring, and when there is a push-off, we release this energy and we inject that energy in the foot. It's a bit the same like a bow and an arrow. You load the bow, and at a certain moment, all this energy goes in the arrow. So like that, you can throw an arrow much faster than you would do it with your hand. But also other universities, like the University of Michigan, are developing exoskeletons, or also at the MIT. This is a famous professor, you heard, that developed his own prosthesis, and this is a very nice prosthesis because this professor got stuck in a blizzard and his feet froze off due to frostbite. So it's the guy with the two shoes, so on the left hand, so on the right here, he's wearing two prosthetic robotic devices. So he was already able to make them very compact so they fit in a shoe, so nobody in fact really sees that he's wearing a prosthetic device. So we at the VB still need to work a bit to make it more compact and be able to fit it in a shoe. So these were all part of medical robots. So there were also different other medical robots in development, like the surgical robot systems, or also they even are investing in brain implants so that directly from your brain you can control robots or computers, or even small robots you can swallow, like this endoscopic leg capsule that you can swallow to have endoscopic examination of your stomach, for example. So I think that robots can really create new markets, so they have an economic value, and it can also answer a lot of societal problems like the aging society. But because I think it's such a strong technology, I think it's also some problems that can rise. So I think besides the technological evolution, we also need to answer the ethical aspects like responsibility. If such a robot car crashes, who is then responsible? Me, while I was sleeping in my car, or the company who produced the car? Or also like privacy, those robots have a lot of sensors. So for example, can I interrogate my robot at home what my girlfriend has done during the day? So that's maybe also things that we need to think of. Or can I hear my children when they are using my robots? Or can the police interrogate the humanoid robot and so on? So also on intimacy, they're now also developing sex robots. So what do you do with that? Also, when we use robots with elderly, some say, yeah, you're not allowed to do that because as such you exclude them from human contact. So there are different issues that need to be solved. So as a conclusion, robots are about to enter our daily life. And I think robots will be kind of everywhere, like we have computers now everywhere in different forms and applications. But there is really still a lot of research necessary. And we also need to think about ethical problems as well. Thank you very much for your attention. And if you have questions, please. I think there's a micro if you have a question or really shout loud. Yes, please. Yes, so this question was that we have a lack of standards, and if there is something currently coming now. I think so. But my opinion changed already over the last year, and then I think, this will become important, this will become important. I think the ROS, Robotic Operating System, is becoming more and more important, like Willow Garage, that's PR2, that is a big company. It has money of the founders of Google in it. So I think when we have a big industry, that will also push a lot the standards, I think. But if you want to start something now, I think now you need to bet on ROS to program it. It has a lot of tools to work with. Another question? Yes, please. Yes. For example, that robot arm that you saw going to the chest of that researcher is now commercialized by KUKA. So the whole prototype went to KUKA and they can buy it. So they also see that the industrial robots now have their limitations in accuracy, and they're mostly position controlled. So you you control the position of the robot. Like for different other tasks, you need to have force control, and this robot is very good in force control. And for example, now Mercedes has bought those robots to assemble their gearboxes, because when you need to assemble the gears in it, it's like putting a pick in a hole. You cannot do it with position control. You really need to do it by force control, and this robot is capable of doing it, and apparently they're very happy with it. So yes, KUKA is also taking more and more ideas from the research to put it in their industrial robots. But they're not yet busy with service robots like vacuum cleaning robots and so on. Okay, I think it's for the next speaker now. Thank you.